All right, here are our intro to fluids and pressure notes here, okay? So in order to start talking about fluids, we got to start by discussing what is a fluid, how do we define a fluid, and the best place to start with that is by talking about the different types of matter, the three different phases of matter. So we start with solids, okay? My super simplified definition for what a solid is, it is matter which has a definite shape and definite volume, okay? So shape is the kind of the size, the form that the matter takes, and that is definite, right? A solid object is going to have a shape to it, right? And that's not going to change. And then volume is just how much space it takes up. So here is my drawing. It's these dots represent the molecules of an object. So these molecules, they're tightly packed together, and they have that definite shape. In this case, it's kind of a square. Then we have liquids. Liquids are similar and different in some ways. So they have indefinite shape, but definite volume. Okay, so here are my liquid molecules in this little square. They've taken up the shape of the, square that they are in, but there is a specific amount of volume. There's an amount of space that they take up that does not change. Then we have gases. Gases are indefinite volume, indefinite shape. Okay, so here's all the gas particles in that square. They are spread out. They are taking up the entire space. So their volume, the volume of a gas can change, right? Depending on if I put it in a different container, right? If I take this gas and put it in a bigger square, it will take up that entire square again. So we say it doesn't have a definite shape, a definite volume because of that. Okay, so then what makes a fluid? Well, our definition for a fluid would be matter with indefinite shape. Okay, so matter without definite shape. If we go back over here, we look at our definitions here of our different types of matter, and we see that both gases and liquids are considered fluids because they have that indefinite shape. So for the rest of this unit, we're going to be talking about fluids. Most of what I say will mostly be related to liquids. That's kind of our focus, but technically a lot of the things we talk about when it comes to fluids also apply to gases. Okay, so a characteristic and very important property of all fluid is their density. We call it a characteristic property because it kind of defines and dictates a lot of the properties and characteristics of that fluid, okay? So let's talk about what density is. Well, density, it has an equation, probably one you have encountered before. Our equation for density is mass divided by volume. Essentially, density is how much stuff is taking up how much space, okay? How much stuff is taking up how much space. Another way you could think of it is how tightly packed the molecules of an object, fluid, gas, or liquid or gas are, how densely packed those molecules are. Units, well, the units for mass are going to be kilograms. Our units for volume, well, that would be meters cubed. So our units for density would therefore be kilograms per meter cubed. Okay. There's lots of different units for density, actually, but that is the one we're going to use most commonly. And then the question is it a vector, is it a scalar? It is a scalar. Density does not have a direction that it points in. It is just a property of that matter. So yeah, density, it's important. It's a characteristic property because we can actually use it to identify substances by measuring density. As long as that substance is pure, a pure substance, meaning it is all of one single, alloy or element or something like that, then we can identify that object by its density. So let me show you an example of this. So here in this example, which should be in your notes, in your guided notes as well, you have a sphere of undetermined material that has a radius of 0.25 meters and a mass of 24.4 kilograms. What is it made out of? Okay, so it asks what it's made out of. I'm going to use density to help us figure out what this object is made out of. So I need the mass divided by the volume. I have the mass already, so I'm all good there, but I don't have the volume of this sphere. I'm going to have to calculate that. So I already have the volume of a sphere written out over here. That is not something you're ever going to have to memorize. If you need the volume of a sphere, it will be given to you. So let's go ahead and solve for that for this case. So the volume of our sphere would be 4/3 pi times the radius, which is 0.25 cubed. All right. So that volume is going to be 0.0654 meters cubed. All right. So I have all the numbers I need now. I have the mass, 24.4. I have the volume, 0.0654. Let's see what we get there. So my answer here is 372.8 kilograms per meter cubed. So now I'm going to take this. I'm going to look at, there should be a table in your notes that has a bunch of different densities of pure substances. And it looks like this density is most similar to the density of pine. So that's a type of wood. So it seems like this sphere here is made out of pine wood. Cool. All right. So we got that out of the way, kind of some basics on fluids. Now let's start talking about pressure. Let's start with our definition of what pressure is. Pressure is the amount of force per unit area. Okay? So a lot of times when we've been talking about forces in this class, we've been drawing them as a single arrow and kind of imagining them as being applied at just a single point on an object. But in reality, that doesn't actually happen, right? When you push on something, your whole hand is applying a force to that object. So it's the amount of force that you're applying over the area of your hand would be the amount of pressure you are applying. So given that, we use this equation, this general equation for pressure. Take the amount of force you are applying and divide it by the area over which that force is being applied. Okay? Units for pressure are going to be kilopascal. Okay, so the base unit there is a pascal, and in general we count them in thousands, so we use the kilopascal. So kilo as in 1,000, pascal as in unit of pressure. Is it a vector? Is it a scalar? We're going to say it's a vector. Pressure does have a direction that it is being applied in. So we are usually going to call that a vector. Okay, cool. Let's do a quick example here. So the example here says that we have a 60-kilogram person standing on their 2 feet, drawn here. How much pressure are they exerting on the ground? Okay, pressure is force over area. So in this case, the force that they are exerting is going to be force of gravity. We have an equation for force of gravity, right? That's the mass of the object times 9.8. So I know the mass, I know G, I know the area, so let me plug in my numbers here. So mass is 60 times 9.8 over 500. So my answer is 1.176. Okay, but wait a second. I do need to make one change here. My bad. Forgot that we need to convert, right? If it's in centimeters squared, well, we need our numbers in meters squared because we always work in meters, not centimeters. So rather than 500 centimeters squared, that is actually going to be 0.05 meters squared. So let's adjust that in our answer over here. So that's 0.05 meters squared. Let me run that calculation again. There we go. 11,760 kilopascal is our answer there. All right. Okay, and then part 2 of this question says, all right, if the person now stood on only 1 foot, what would the pressure be under that foot? Okay, so they are lifting one of their feet up. So if that is only 1 foot, that means we're actually going to just take that area and divide it in half, right? So it's going to be the same exact calculation, but with half the area. So rather than 0.05, it's going to be 0.025. And that is going to double our previous answer up to 23,520 kilopascal. Cool. All right. Moving on, now we're going to talk more about pressure from fluids, okay? So a fluid exerts pressure in all directions, right? When you go underwater, you don't just feel pressure from above you, you don't feel pressure from below you, you feel it all around you because the water is surrounding you. Essentially, think of it like when you hop in a pool. The space that you are taking up in the pool is an area where the water used to be. And the water wants to go back there. It wants to go back into the location it was before, so it is pressing on you, it is pushing on you, trying to move into the space that you are in, but because you're a solid object, you're not going to move, so therefore it is applying that pressure to you. Now, when there is a solid object, that fluid pressure is always going to act perpendicular to that solid surface. Right? So look over here on the right, I have this drawing of a square in, we'll just call it like a cup of water. So if I'm looking at the right side of my square over here, the fluid will press to the left. The left side of my square, the fluid will press to the right. That pressure is pressing to the right. On top, it'll press down. On bottom, it'll press up. The flat face of the square, the cube that is kind of in parallel with the screen of that you're looking at right now. So that is going to have a force pushing inward, pushing into the screen, because that is going to be perpendicular to that solid surface there. So you are being pressed in from all sides by a fluid when you enter, when that object is in a fluid. Okay, let's look at some data from the lab yesterday. So the lab yesterday, we all got pretty solid data. We put depth on the x-axis and pressure on the y-axis, and you should have gotten pretty linear looking data, meaning that as the depth increases, so did pressure. That was something that we kind of predicted. We kind of knew already that as you go deeper in water, you experience a higher amount of pressure. We can use that to start building out our equation for pressure from a fluid. The first thing that we're going to add, we know that as depth increases, pressure increases. So let's add depth to this equation. So we're going to use H to represent depth. Depth meaning how far below the surface of the fluid you are. Okay? So, if you're hopping into a pool of water, it's how far below you are below the surface of that pool. Okay? Other factors that are going to affect it. Think about if you were in a more dense liquid than water. If you were in a more dense fluid like, let's go with like honey or something like that. That is more dense than water, right? That is going to press down on you more than if you were just in a pool of water, right? So we are also going to include density in our equation here, okay? I'm going to use the Greek letter rho to represent density, okay? So I was using D before. I'm switching to a new letter, so that's going to help us later. But we're using this letter here. This is the Greek letter rho. It kind of looks like a P with a little tail. It represents density, okay? And then finally, we're also going to include G, because if you were on another planet, you would feel different amounts of pressure because of that different amount of gravity from it. So G, that's just 9.8 like usual. Okay, so there you go. this is our equation for pressure. All right. Very important though. Add a little extra bit here. This is only for fluids of uniform density. Okay? Pretty much all of the fluids we'll talk about in this class are of uniform density, so you don't have to worry about that. But this equation doesn't work if you have a fluid that is changing density throughout. Like the ocean, most of it's going to be of similar density, but there are some parts that are more dense, less dense, so we can't use this equation for all parts of the ocean. Okay, sweet. Last couple of things we got to talk about here are the three types of fluid pressure. The first we call atmospheric pressure. We use, in parentheses here, I've written P subscript 0. That is the kind of symbol we use for the atmospheric pressure. What is atmospheric pressure? It is the pressure from the gases on the surface of the Earth. So you know that the Earth has this atmosphere surrounding it, full of oxygen and all these different gases, and that is a fluid. So therefore, it is in fact pressing in on you. It is applying pressure to you. You don't notice it because you have lived your whole life with that pressure, and your body is designed to essentially ignore it. Your brain is designed to ignore it, but there is pressure from the atmosphere around you. At sea level, our atmospheric pressure is about 101 kilopascal. And that changes depending on how high up you are above sea level. So there is less pressure if you were to go to, say, Colorado, which has a high elevation. But at sea level, it is 101 kilopascal. Okay, up next we have gauge pressure. Gauge pressure is the amount of pressure from a fluid other than the atmosphere. So when we were doing our lab where we were measuring the pressure from the depth under the water in the graduated cylinder, that was gauge pressure that you were measuring, not necessarily atmospheric pressure. And then finally, we have absolute pressure. Absolute pressure is just the total amount of pressure. So you add your atmospheric, you add your gauge, and that is your absolute pressure, okay? Because technically, if you hop in a pool of water, yes, you are feeling the gauge pressure from the fluid itself, but also the atmosphere is pressing down on the fluid, which is pressing down on you. So that absolute pressure is what is that total amount of pressure that you're actually feeling in that moment there. Okay? All right. Next up, final thing, we have a couple example problems here. So example problem 1 says a 40-centimeter tall glass is filled with a vegetable oil to a depth of 30 centimeters. The density of the vegetable oil is 80 kilograms per meter cubed. What is the gauge pressure at the bottom of the glass? Okay, so we know, we know density is 800 kilograms per meter cubed. We know that the depth is going to be 30 centimeters. Okay, so we're going to calculate gauge pressure. That is density times G times H. And in this case, we know the density is 800. G is always 9.8. And the depth is 30 centimeters. I'm converting that to meters and calling it 0.3. My answer there is going to be 2,352 kilopascal. Okay? And then it asks, what is the absolute pressure at the bottom of the glass? Absolute pressure is your atmospheric pressure. Atmospheric pressure plus your gauge pressure. We're going to assume this is at sea level. So we're going to say that our atmospheric pressure is 101 plus our gauge pressure, which is 2,352. That adds up to a total of 2,453 kilopascal. Okay? And then our other example, our final example problem here says, calculate the absolute pressure at an ocean depth of 1 times 10 to the third meter, so that's 1,000 meters. Sorry, depth is 1,000 meters. Assume that the density of the water is, so our density is 1.025 times 10 to the third. Okay, so that's 1,020 kilograms per meter cubed. And atmospheric pressure is 101 kilopascal. Okay, cool. So we're finding the absolute pressure at that depth. So let's start by finding our gauge pressure first. So that is going to be density times G times H. Density is 1,025. G is always 9.8. H is 1,000. Okay, so that comes out to, ooh, that's a big number. Okay, that is 10,309,600 kilopascal. And then we need to add that, so we got to find the absolute pressure, so that is gauge pressure plus atmospheric. Gauge is that big number. Plus atmospheric, which is not going to make much of a difference here because we have such a big amount of pressure. Our final answer is, sorry, that should be, this number here is 101, not just 100. All right, so our final answer here is 10,309,701 kilopascal. So if you go 1,000 meters deep under the surface of water, under the surface of the ocean, you are going to find that much amount of pressure. This is kind of why we as humans aren't able to go that deep underwater, because that is a deadly amount of pressure right there. Okay, cool. So that covers all our notes: intro to fluids, intro to density, intro to pressure. Hope this was helpful. I will see you guys later.